Yeah, so we are discussing this D problem, and technically there is a grid and there is a light bulb which is initially turned on. Over here there is a pressure hidden, right? So there are a lot of operations which is applied on this grid so that we can kind of not reveal the location of this original pressure, right? So what we do is we select a point, let's say x comma y. So on first operation what we do is we turn on the light bulb at x comma y, and then we turn on the light bulb on its adjacent square, and then we also turn on the light bulb on the adjacent square below, and we turn on the light bulb on the adjacent square diagonally, right? And we turn on the bulb at x comma y too. So initially only this bulb was on, that is where the pressure location was hidden. So I am marking it this way. And now we are turning on all these. Now the question says that if an operation is applied, let's say on this square, right, that is x dash comma y dash, what happens is this would produce the same effect, but the issue is when it's trying to turn on the light on the adjacent square below, it is already turned on from the previous operation, right? So this time it will turn this off because this is already on. So it's like switching the states. If it's turned on, it will turn it off. If it is turned off, it will turn it on. So this will be off, and then it will try to produce an effect on the adjacent square to the right, but it will turn this off again, and then it will try to produce an effect on the adjacent square diagonally, but it will turn it on this time, right? So in the end, only this bulb is turned on, this bulb is turned on, and this bulb is turned on, right? And our original is turned on. But one last time, let's say an operation is applied here, okay? X double dash comma y double dash. This will also affect our original pressure location, right? So now it will turn this off, it will turn this on, it will turn this on. Yeah, so these are the final locations of the turned on light bulbs. Okay, the grids where I have ticked on. So now the question has given you, the input of the question has given you the turned on light bulbs at this point. And you would have to find the location of the original hidden pressure from the turned on light bulbs. So like, originally this question has some mathematical, geometry or some solution like that, and it is a 2000 paper problem, and I had to even look at the editorial, so I found a great solution which I'll try to explain it here since there is no good explanation is given in the comment section. So technically the thing is, there is this one user who brought in bitwise properties over here and solved this very easily. So you can solve this like in 4 lines of code or 5, something like that. So for this we will have to know a very important bitwise property related to Xor. So first is, before I say what the property and everything is, first if you make an observation over here, right, you see that initially when we applied this operation on x comma y, this bulb was turned on, right? When we applied the first operation, it was turned on. But the issue is when we applied an operation on x dash comma y dash, it produced an effect on x comma y which turned it off. So basically 2 operations were applied on x comma y, right? So in the second operation it would be off. So you can see a pattern that, okay, on every odd operation, it would be turned on, and on every even operation it would be turned on. Right. So on a particular position, any random position x comma y, if an operation is applied even number of times, it is turned off, and if it is applied odd number of times, it is turned on. So that is like one observation. So this is like, switching the states, and Xor is used to flip the bits, right? So if you take 0 or 1, and if you Xor it with 1, it will automatically flip the bit. So that is first how we can try to connect Xor with this problem. But still, how do we use it? How do we use it to find the original pressure location? That is a trick. So now observe this. Okay, we know this Xor property like Xor x is, what is it saying? What is
0.
X? 0, right? Awesome. Yes. This is 0. Xor X is 0. Now I'll ask you one question for you, okay? This is like basically just a number, right? What if I applied this Xor on a vector? Like, for example, okay? Let's say 2, 2 Xor 2, 2. This should also be 0, obviously. Right. Now let's say I have a set of numbers like 2, 2, 3, 3, and 2, 2 again. If I Xor everything, each of these elements in this vector, what will be the final result? Any guess for it?
2 2 with 3 3 and 2 2 with again 2. You are asking like that?
Yeah, if you saw everything here, like if you saw everything,
Oh,
what will be the final result?
3 3.
3 3, obviously, right? Because 2 will cancel out 2 from this property, and the Xor is associated commutative and all. So answer is going to be 3, 3. But why do you say it's 3, 3? That's what we have to think about. Why did it
Because it occurred odd number of times.
Yeah, because it occurred odd number of times and this occurred even number of times. But from this we can generalize something, okay? I'll tell you what we generalize. Basically this is true. Okay, this is always true. We can kind of generalize this operation into this particular way. Okay, you see this. Technically what we did over here, we can simplify this as 2 Xor 3 Xor 2, comma 2 Xor 3 Xor 2. It's like you're first solving for all the x coordinate and then you're solving separately for all the y coordinates still to give the same result. 3, comma
3.
We can observe this for anything. You can give me any vector, any 2D coordinates, and you will notice that if you try to Xor everything right, it will break down to Xoring all the x coordinates and all the y coordinates. Right. So this is like the main property which you have to understand. Now this problem will become easy. I'll show you. Let's just see what operations are given. Okay. So, like first, the operation is on x comma y according to the question, and x comma y plus 1. Then x plus 1 comma minus 1. And x plus 1 comma y. So these are the 4 operations, right, which we can apply in this problem. Now the trick in this problem, right, or any type of problem where there is certain number of operations, okay, like these, we have to find something known as the invariant, okay. Do you know what invariant is? Okay. What is the meaning of variant? Do you know?
It's
something that will change, no?
Yeah.
So invariant means something that won't change. A property or an observation associated with the problem which does not change. Okay? We have to find the invariant. Right. And also from the earlier observation I told that in 2D coordinate system, when you try to Xor all the coordinate points, you can break it down to the Xor of all the x x-axis is x coordinates individually and all the y coordinates, right? And your final result or the final coordinate that you get will be the solve of all x and solve of all y. If you observe over here, with these four operations, right? When you solve all the x coordinates in this operation, don't check it on any numbers, okay? See, I took this x XOR, this x XOR x, and this x XOR x plus 1 XOR this x plus 1. What do you think would be the answer?
0.
0, right? Did you notice this? So for any coordinate of x you take, right? For example, in our problem, in our problem, let's say operation is applied on 3, 4. Okay, 3, 4 coordinate. Its effect will be where on? It will be on 3, 5, right? And it will also be on 4, 3, and it will also come on 4, 4.
4.
In all these locations, its effect is going to be produced, right? But if you take the XOR of all the x coordinate, this is equal to 0, right? Always. In this problem, that is an observation. If you take the XOR of all the x coordinate, it will be 0. But the issue is when you take the XOR of all the y coordinate closely, y XOR y plus 1 and then XOR y minus 1 XOR y. Here like what happens is there is y occurring 2 times, so y and I will cancel. That is obvious, but issue is this both won't cancel. We can't, so answer is going to be y plus 1 so y minus 1. So this is variable. Like for example in this case, like if you take the XOR of all these y axes, 4 and 4 will cancel, but 5 XOR 3 will be something, right? It will be something. Similarly, the answer of 5 XOR 3, maybe in another situation, maybe you will get, in another situation. Anyways, the difference between y plus 1 and y minus 1 is 2, right? So, anyways, the difference between the final two numbers will be 2, because 5 and 3 is 2. So, 5 XOR 3 will be some value, but it doesn't mean 7 XOR 5 will be same value as 5 XOR 3. It will always be different. So, answer to the XOR of all the y axis is different. This is different. This is same. Answer to the XOR of all the x is always the same. But the issue is, like I said, focus on the invariant, right? This is invariant. Same means what? Invariant, right? It doesn't change. But y changes. But if there is a changing property, right? See, what is the main idea of generalizing something? Generalizing a formula. A formula should always give the same result, right? Technically, for a similar observation, the result should look the same. The pattern should be the same. That is called creating an invariant. An invariant will only give us proper results. When there is a variant like this, right? We can't generalize and we won't be able to solve the problem, right? So over here, somehow, now what we have to think of is, somehow we have to make the y-axis an invariant. How do we do that? See, if we get x-axis invariant and y-axis invariant, no, we'll be easily able to find the treasure location. Because there is 2 invariants, so we can generalize and we can find it.
But how?
I'll tell you how. This is the trick. Wait. I need to make y-axis invariant. Anyways, I can't make. Right? I just can't make whatever shit I do. So I'll do something else. So all the value of x's x comma x is there and x plus 1 is there and x plus 1, right? In these four coordinates the thing is applied. Coordinate the effect is applied, and in y you have y plus 1, y minus 1 and y, right? Now observe something, okay? Imagine if you had taken x plus y. So if you take x plus y, just say x plus y is what? X plus 1. Right? So x plus y is x plus 1. What is x plus y plus 1? X plus y plus 1, right? Right, obviously. What is x plus 1 comma y minus 1?
X plus 1. Sorry, x plus y.
X plus y. Now see, what is x plus 1 and y? It is x plus y plus 1. Now do you see? 2x plus y and 2x plus y plus 1. If you take the XOR of all the x plus y terms,
Cancel. 0.
it will easily cancel. If you take a XOR of all this, right? If you take a XOR of all these terms. So, right now in our input, right, in the given question. One second. I will not this also. No, I should not write this. X plus 1, comma, y minus 1. What was the last coordinate of the
X
plus 1,
comma
comma, y. Parallel. So right now our input is given as x comma y, right? This is how our input is given. We can transform this coordinate. This is called transformation. Okay? X is invariant but y is variant. But we have to somehow make this invariant to formulate something. We can transform this to x comma x plus y. Simple. Which means if you are given a coordinate 3 comma 4, right? We can transform this to 3 comma 3 plus 4, that is 7. But I tell you why, you will think, okay, if you transform, answer will change, right? That is a confusion, right? Final answer, how is this possible? This doesn't make any sense. It will make sense. Wait, I'll show you how. So, we notice that when you take x plus y, all the
that is
it's all. No, what happened?
no.
So, I'll tell you now. Okay. Basically, once this is also invariant, right? We have transformed this coordinate into 2 invariants. Now the thing is, since we transformed it into 2 invariants, those elements, I'll tell you the property about invariants, okay? Only an invariant, see, the Xor property which I showed you, right? X XOR x, that is x XOR x is equal to 0. This is the property of Xor. There are 2 x over here, right? That is even. There are even x's over here. Similarly, if I extend this property to x XOR x XOR x, there is odd x's, right? There are odd x's. So it is what? 1. No, it is x. Answer is x, right? So in these both, right? Which means XORing of all the x's. What is the invariant?
First one.
Huh?
First one, even.
No, invariant, like what is the property which is the invariant in these both examples? Invariant is parity.
Yeah, even and odd.
Parity. Parity will not change. Parity is an invariant. That is what is an invariant.
Okay.
Based on the number of x's. Parity is a property that is invariant. So the thing is, right, since we made both our x and x plus y both are invariants, when you apply the XOR operations on all the coordinates, Which means if you have 3 inputs, that is 3 comma 4, maybe 5 comma 4, and maybe 3 comma 2, and 5 comma 2. Over here, no? If you see all the invariants, right? 5 and 5 is getting applied 2 times. 3 and 3 is getting applied 2 times. So everything, a final x coordinate will be 0. For sure. Everything is cancelling with that. And now you see these are y-axes, right? The y-axis is not an invariant, so you can't take a Xor of all this. Instead, you will have to transform y to x plus y, right? So x plus y is what?
7.
4 is 4 becomes 7, no? This 4 becomes 9. This becomes 5. This becomes 7, right? Now you see. Now 7 and 7 will cancel. So our final location, right? Where the light bulb will be on. When you Xor all these, no? Those light bulbs which are even number of times will turn off. Where operations have been applied on it, even number of times will turn off. And those light bulbs which is where operations have been applied all number of times, that will turn on. So the thing is, this is 9, Xor 5. In this coordinate, this is the coordinate that we got. Because this is an invariant property, we got this coordinate. But this is not where the hidden pressure is. Because we did x plus 5. Okay, we have transformed the coordinate system. We need a correct answer in x comma y. This is a transformed coordinate system to make things invariant. So Xor property can be applied. Xor property can't be applied if there is no invariance. Okay. Now, this is in a transformed coordinate system, this is the answer. But in our actual coordinate system, what is the answer?
Minus x. The coordinate, y coordinate should be subtracted by x.
So minus x, right? Exactly, that is the correct answer. So basically the thing is over here, you took Xor of all the x's, right? Like, what we did was we took sigma, I'm telling Xor, okay? Xor of all the x's. This is Xor, not sigma, Xor. And we took Xor of all the x pluses. Now what we need to do is simple. From x plus y, we just need to subtract all the Xor of all the x's. So Xor of y, we can write it like this, okay?
Okay.
Xor of all the y is equal to Xor of all the
x plus y minus Xor of all x.
Simple. It works, just works. So basically the answer is, what is Xor of all x? 0. This is 9 Xor 5. So your final answer would be 0, 9 Xor 5 minus 0. But if there was an example, something like, maybe there was one more thing, 3 comma something like one more value, right? Maybe this would have been some other value, x would have been some other value, so you would have to minus
that value.
That value. So this is where the final pressure location is given. This is one to see. The issue is, right, in this problem, since the final light bulbs are given, final locations of the light bulb are given, there is many possibility for the position of the hidden pressure. Right? If you think about it, there is many positions for the possibility of a hidden pressure that could produce the same final result which is given. Out of that, one of the positions is this. You get the point, right? Is it clear to you, this problem? Make sense, no? Cool. So this is how we do it. Technically you have to use this. So in the end, our final answer is anyways, final answer is Xor of all the x, comma, Xor of all the x plus y minus Xor of all the x. This is the final answer.